Alright. Welcome back to another video, ladies and gentlemen. In this one, we're going to be building EfficientNet completely from scratch. And if you haven't watched my paper review video, I do recommend that you watch that one first, where I kind of go through the paper and show all the important parts so that you get a good understanding of the model. I think you can still follow this video even if you haven't watched that one. But there are probably some details that might be difficult. But anyways, let's get started. All right, so let's start with the imports. We're going to import torch, import torch.nn as an n. From mat, import seal. All right, and those are the only three imports we're going to use. Now we're gonna specify some details of the base model first of all. So if I bring out the paper, and for those of you who watched the paper review, this is exactly what I went through. But this is the base model right here, and all I want to do first of all is just to write down all of these specific information. So the layers right here, the expand ratio, which is this 1 and this 6. Then the channels, I want to write up the kernel size and the strides and so on. All right, so from that, just that table, we're going to build a base model, and the base model is going to be a list of lists. So the first one is going to be, so it's going to be expand ratio, it's going to be channels, repeats, stride, and kernel size. All right, so the first value right here is going to be 1. That is this one right there. Then we're going to have the channels, which is going to be 16. So we're going to start with the MB conv. This one we're just going to do later on, but we're going to specify all the details for this MB conv. All right, so I mean, the channels is going to be 16. The repeats is going to be 1, stride 1, kernel size 3. All right, so let me just, all right, so the repeat is this 1 at the end here. That's the number of layers that we're going to use this mbconv 1. And yeah, the channels is from this one. So everything is from this information. I'm just going to write down the rest of these, and you can look at that table to look at the details. All right, so that's what the base model looks like. We use expand ratio 1 and 6. This is the channels, just that list. The repeats right there, the stride. So sometimes there's a stride of 2 if we down sample the height and the width. So we divide it by 2 essentially. And the kernel size is 3, but sometimes it's also 5. So that's the base model. Then, we want the 5 values for each of them. So 5 values, it's going to be a dictionary. We're going to set B0, B0 like that. We're going to set a tuple, and the first is going to be the 5 value. And so this was a little bit tricky. I had to do some Googling to find that out exactly. And it's not clear to me exactly how they did it for the resolution. So, they use this alpha, beta, and gamma values. And then what you would do is you would take, to get the, let's see, I think so for example, to get the depth, you would do alpha raised to phi, like that. And pretty much for the same thing for the others. But this one is for the resolution, this one is for the depth, and this one is for the width. All right, so this is how you calculated it, but I didn't get it to work for the resolution. There's something funky, and I saw other people have problems with this as well. But anyways, the 5 values that I were able to calculate, which wasn't clear from the paper, and after some Googling, the first one should be 0, and the resolution, I'm just going to write that. So in the tuple, it's 5 value, it's resolution, and then it's drop rate, all right? And so the resolution is 224 for the base model. The drop rate is 0.2. So B1, the alpha, the phi value is 0.5, the resolution is 240 and 0.2 drop rate. So again, these ones are pretty so if you use those, it matches the depth factor and the width factor that they used. So yeah, I'm just gonna write those up, but it was a bit tricky to actually find what they were. B2 is 1 and then 260 0.3 drop rate, and now it follows a pretty nice pattern. So B3 is 2 300 0.3, and I'm just gonna fill out the rest of these. All right, so what have we done now? Well, pretty much nothing, right? We just set up the base model parameters, all we're gonna need, and then the 5 values, the resolution for each of the EfficientNet models, and then the drop rate, which increases as we increase the model of the EfficientNet. All right, so let's actually get started, right? And what we're gonna do is we're gonna first do a conv block. All right, so let me just do pass right now. We're gonna use a conv block. Then we're gonna use a SqueezeExcitation, right? And I talked about this in the paper review, but I'll talk a little bit more about it later on. This is sort of a trick that they used. And so we're gonna use the CNNBlock. The CNNBlock is just gonna be conv batch norm relu. So pretty standard. And then after the SqueezeExcitation, we're going to use an inverted residual block. Again, I talked about this in the paper review, but you might understand it from just the implementation as well. So that's what we're going to use. And then lastly, we're going to create the EfficientNet model, right? And the EfficientNet model is going to use all of these three, obviously. But so let's sort of start from the most basic, and then we'll build our way up. So with the CNNBlock, right? This is not going to be, I guess, anything too difficult. So I'll go a little bit quickly here, I guess. So we're just gonna we're gonna take in some in channels, some out channels, some kernel size, stride, padding. And then we're also going to take groups, and I'll explain what that is as well. So for those of you not familiar with groups, actually I'll take that in just a moment. So we'll do CNNBlock dot init. Yeah, and then we'll do self.cnn is nncom2d, in channels, out channels, kernel size, stride, padding, right? This is going to be pretty general. So we're just sending in those. We're going to do a conv, and then we're going to specify groups to be groups. And so what this is for is what I talked about in the paper review, which was depth-wise convolution. So normally when you have a convolution, you would have a, let's say a 3x3 kernel, then it would be a cube. So it would be 3x3x3, so it would span across 3 pixels height, 3 in width, and then 3 in channels. But if you want to do a depth-wise, then you would do a kernel size of 3x3 for each filter or each channel independently. So that's what we specified the groups for. So in that way, the kernel size of 3 doesn't become a cube, it just becomes sort of a 2D 3x3 sort of region. But anyways, so that's what that is for. And then we'll do a self.backnorm is nn batch norm of out channels. And for the activation, we'll use silu as they used. So I don't know, you might be familiar with this, but there's silu is the same as swish. I think this was used in a paper first, and then swish was used, but they're the same thing. And I think this is the first one that came out, so that's the name I'll use. All right, so then we'll define forward of x, and all we'll do here is return self.silu. I'm not sure how you pronounce that actually. anyways, we'll use that. And then, so batch CNN, and then batch norm, and then that activation function. All right, so that's it for the CNN block. We can do the SqueezeExcitation, which we will use inside the inverted residual block. What this is for essentially is to compute attention scores for each of the channels. And so this is from the squeeze and excitation paper, but we're taking some in channels. We'll have some reduced dimension at the middle. First, let's call super of this .init. So what we'll do is we'll do self.squeezeExcitation. SE is NN sequential, and the first thing we'll do is NN adaptive pool. So the adaptive pool will take the height and the width of whatever comes in, and we're just gonna give one value as output, right? So if the input was, let's say it was, some example, right? So we have some channels times height times width. This is going to be channels times 1 times 1. So we'll just have a value for each channel. Then we'll do a NNCom2D, which will take in some in channels to some reduced dimension with a kernel size of 1. Then we'll do NNSilu, and I hope this doesn't fuck with my recording because I'm exporting a video. I really hope this is not gonna do anything bad. All right, so then we'll use Silu, and then we'll use another com2D, and we'll bring it back. So reduce dimension to in channels and a kernel size of 1. And in the end, we're going to use sigmoid. All right, so what did we do here? Well, we first did this, right? Just have channels and then a value for each channel. Then we did a com2D that takes it from the in channels to some reduced dimensionality. So some reduced number of channels. And then it does an activation, and then it brings it back. And then at the end, we'd use a sigmoid. All right, so what this is we're gonna, for each channel, we're gonna have a value between 0 and 1. And so the idea is that these are sort of attention scores, if you're familiar with attention models. And then we do return x times self.se of x, right? So for each channel, it's gonna be multiplied with the value that comes out from this sequential of all these com layers, which gives us a value for each channel of how much that channel is prioritized, essentially, right? How much should we prioritize the values inside of that channel? And that's pretty much all that it tells us. Okay, so now that we have that, we can go to the inverted residual block, and all this is going to be, we're going to use self. All right, so we created our init, and inside this we're gonna have self, in channels, out channels, some kernel size, stride, padding. We're gonna use expand ratio, right? So what it does is that it takes some input, it expands it to a higher number of channels. It uses a depth-wise convolution, and then it brings it back down to that same number of channels as it was from the beginning. And so we'll use some reduction for, so this is for the squeeze excitation right there. That's for the reduced dimensionality. So we'll reduce it by 1/4 of whatever comes in. And then we'll have survival probability. And this is for, so let me write it. So this is for squeeze excitation. This is for stochastic depth. That's how you spell it. So we'll get to that when we, if you haven't watched my paper review video. But so super inverted residual block self of init. So let's just self survival probability is 0.8. Then we'll do self.use residual. It's going to be true or false, and it's going to be true if the in channels is equal to the out channels and the stride is 1. So if we down filter, or if we downsample, then we can't use a skip connection, right? Because the height and the width won't match. If the in channels is not equal to the out channels, then we can't add them either, right? So that's sort of the operation. So if both of these are the case, then we'll use a residual connection, and then the hidden dimension. So we'll do hidden dimension is going to be in channels times some expand ratio, right? So that's going to be the hidden dimension, sort of in the middle of the residual inverted residual block. Then we'll do self.expand is going to be if the in channels is not equal to the hidden dimension. All right, so this happens, I guess. So I guess this happens for every first of these layers right here. So in the beginning it's 16, then it becomes 24, right? So in between those two, it's gonna expand. But then for the second layer, it's gonna sort of be the same. So in between these all these stages right here is when we'll actually expand it. So if that's the case, we'll expand it. And then the reduced dimensionality is integer, so we're gonna just floor it to in channels divided by reduction. All right, so what we'll check now is if self.expand, right? So if we are going to expand, let's create an expand com layer, CNNBlock. And so we're reusing what we created up there. And all it's gonna do is it's gonna expand the in channels to some hidden dimension. And again, we're going to send in the kernel size to 3, stride of 1, and padding of 1. All right, so that's the expand comp. Then we're going to use the inverted residual block. So it's just going to be NN sequential. It's just going to be a CNN block first of all, of some hidden dimension to hidden dimension, some kernel size, stride, padding. And then the groups is going to be hidden dimension. All right, so that's going to be that is going to be a depthwise convolution. All right, and then we'll use a SqueezeExcitation in between that. And again, this is just sort of a intermediate step, which does some. It doesn't change the input at all. It doesn't change number of channels. It just sort of gives a better weighting of which channels to actually prioritize, I guess is how you could explain it. And then we'll use conv2d, hidden dimension to out channels 1, and then we'll set bias to false. And I guess we could do that over there if I didn't do it already. So in this right here, since we're using batch norm, right, we should set bias to false. Sort of an unnecessary parameter. So yeah, that's it, I think. So let's go back. We're going to use a conv2d, and then we'll use a batch norm here as well. So and then batch norm 2d of out channels. All right. So this is how the inverted residual block is going to look like. And you can take a look at MobileNet v2 or the paper review if you want even some more information about this. Another trick we're also going to use is actually the stochastic depth. So we're going to create a function. Let me just make sure. Yeah, so we're going to create a function called stochastic depth. It's going to take in some input x. And we're first going to check if not self.training, we're going to return x. So what it does is it's essentially you could say a form of dropout. It's sort of like dropout in a way, but what it does is that it randomly removes a certain layer, right? So, but not during training or not during testing. If it's testing, then we're just gonna do compute between all of the layers. But sometimes we're going to skip some layers with stochastic depth. So specifically, we're gonna compute a binary tensor. We'll do that with torch.rand of the batch size, and then we'll do 1, 1, 1. All right. So this is for channels, the height and the width. We'll set device is x.device. All right. And then what we'll do, so this is going to be values between 0 and 1, right? We're going to do, if this is less than the survival probability, then it's going to be 1. And if it's higher, then it's obviously going to be 0. So that's going to compute a value of 0 or 1 for each example. So then we'll first do if self.useResidual, then we'll return self stochastic depth. No, sorry, this is in the forward. Yeah, sorry, I'm confusing you now. All right, so don't matter anything I did here. So we computed the binary tensor, right? Now what we want to do is we want to multiply that with x. So we're gonna do x times this binary tensor. Now, one thing is that obviously if we sometimes drop the layer of that one, then that's going to change the sort of the mean and the standard deviation and so on of the inputs, right? So to compensate for that during test time, sort of similar to dropout when you rescale the weights and so on, what we'll do is we'll divide towards the divide of x with self.survival probability. And I can't say that this makes total sense to me. When I think about it, it doesn't it doesn't really make, but I guess that what does make sense is that in this way we're sort of maintaining the magnitude of the mean and the standard deviations in the batch. But yeah, this is from the stochastic depth paper, and I haven't read that in detail, but this is sort of just a trick that they use, so I wouldn't put too much emphasis on just this single part. But anyways, for the forward method, we'll take in some inputs, and we'll do x is self.expand_conv of inputs if self.expand. Otherwise, we'll just take x to be inputs. All right, so the first thing we want to do now is we want to check if self.useResidual. If that is the case, then we want to return self.stochastic depth of self.conv of x, right? So we're sending it through a conv layer, which is the inverted residual block, right? That's the entire thing that we did up here. And then we're using the stochastic depth, meaning we're gonna sort of remove the output for some of them. So some of them are just gonna be 0, some examples. But to make sure that we don't lose all of the information, right, we're gonna add the residual connection here as well. And if we aren't going to use a residual connection, right, if we either downsampled or if the channel changed, we're just going to return self.conv of x. So then we're not using any stochastic depth. All right, now we've done the tricky part. All right, if you follow, you might not follow completely, but if you follow, but if you're with me so far, we've done all the complicated parts. So let me just do a quick review. We computed, first of all, we set the values from the paper, right? This is just some details. Then we did the CNNBlock, which we reuse quite frequently, so it saves on some sort of not making it too much code. Then we're using the SqueezeExcitation, sort of attention mechanism for the channels. Then we're doing InvertedResidualBlock, and yeah, so that's the expanded with the depthwise convolution, with the SqueezeExcitation trick as well, and then another conv2d. All right, and that's it. So that's all we did. Now for the EfficientNet, we're gonna do the fun part. All right, so we're gonna do init, and then here we're just gonna specify the version and the number of classes. We're gonna call super of EfficientNet, comma self, and then dot init. All right, so what I want to do first of all is compute the width factor, the depth factor, and dropout rate. So we're gonna calculate factors, right? So how we do this is from the alpha and beta values. The resolution we already have, so we're not using the gamma one. But so if we just create that, calculate factors, we take in the version and some alpha value, right? That's 1.2 from the paper, beta 1.1. This is for the depth scaling, and this is for the width scaling, right? So this is how many layers we should increase. The other one is how many channels we should increase as we increase the number of the model size, essentially. All right, so first we got to get the phi value, right? The value that we're going to take alpha raised to and beta raised to from the paper. So phi, the resolution and drop rate is phi values of version, right? So that's what we did all the way up here in this, where is it? In this dictionary right there. So we're taking out the tuple of those values. Then to actually compute the depth factor, we're going to take alpha raised to phi, right? So this is sort of the phi is dependent, right? The alpha just is constant, but the phi is actually dependent upon the EfficientNet model. So the depth factor is how much larger the channels should be, and the depth is how many layers we should increase for each stage. So let me be specific. So this, for each stage, right, we're going to compute how much should the number of layers right there, how many times should that increase? And then the channels is going to increase as we make the model larger, and we'll do that with the width factor. So we'll take beta raised to phi, then we'll return the width factor and the depth factor and the drop rate, like that. All right, so that was the init part. Nothing too difficult here, right? And then we're doing the last channels. It's going to be math.ceil of 1280 times the width factor, or actually just ceil, right? So just ceil. All right, that's the last number of channels. That's the one right there. So we're doing that one as well in the init. Then for the, we're going to use a pool and an adaptive pool, again of 1. So it's just going to down filter to 1, right? The output at the end is going to be 7 by 7 in height and width. We're just going to run that through an average pool. So adaptive average pool, if you're not familiar, it just makes it to whatever resolution, whatever size we set in here. So 1, just going to set it to 1. Then we're going to do self.features. We're going to create a function for that. So create features of width factor, depth factor, and last channels. All right, so this is pretty much going to be the entire network. So that is going to be a large, big function. So it's going to be important one. And then the classifier, it's just going to be NN sequential of NN dropout, right, of the dropout rate, which depends on the model. And then NN linear of last channels of num classes, right? So that's it for the classifier. What we want to do now is actually create the features. So that's the last part of this model. So we're going to define create features. We're going to take the width factor, how much we should increase the channels of each stage, the depth factor, and then the last channels. All right, so the first channels is going to be int of 32 times the width factor, right? So if the width factor is 1, that means that we're just sort of at the initial model. So if we open that up, we can see here that initially it's channels 32. But if we increase the resolution, if we increase the depth factor, the channels is going to increase as well. So we're going to take, and we're going to take the floor of that with int. Right? We can't have a float value for the number of channels. So that's going to be the channels. The features, we're going to add a CNNBlock of 3 input channels, 2 channels, kernel size of 3, stride of 2, and then padding of 1. Then we will specify the in channels to be channels. And now we're going to iterate through all of these stages. And that's going to be in the base model that we created, the first thing that we created actually. So we'll do for expand ratio, channels, repeats, stride, kernel size in base model. So, all right, we're going to do out channels. And really all we're going to do here is int of channels times width factor. Now that is going to work in most scenarios, I think, but in some cases, if we scroll up for the SqueezeExcitation, right, we divide, we have a reduced dimension, and we do that by dividing with the reduction right there, right? So the reduced dimension is in channels divided by the reduction, which means that it has to be modulus 4, modulus the reduction. So we just want to make sure that the out channels here is actually divisible by 4. So we're going to do 4 times math.ceil of int of channels times width factor divided by 4, right? We're not going to do math.ceil, so just ceil like that. So hopefully that makes sense, right? We're taking this to an integer, we're dividing it by 4, then we're taking ceil of that, and then we times it by 4. And that way you can sort of do some math on that, but it's going to make sure that it's always divisible by 4. All right, for the layer repeats, we're the number of right, so we're increasing the depth. We're increasing the width with the out channels here, but then we're increasing the number of layers also at each stage, and that's going to be ceil of repeats times the depth factor, right? So that's the repeats right there. All right, then we're gonna go through 4 layer in range of layer repeats. So for each layer in the range of, for each layer in layer repeats, right? I'm not sure which, yeah. Layers repeats. All right. So what we're doing then is we're gonna append to that sort of that list, that features list. And we're gonna append an invertible residual block, and we're just gonna send in some in channels, right? We get that from up here. Then we're gonna do some out channels, and the expand ratio is gonna be expand ratio. The stride. All right, so let's see if I'm not missing anything here. All right, so the in channels is just going to be what it is up here. Then the out channels, which we compute right here, right? So after this, we're going to do in channels equals out channels, and then it's going to go through each of. It's going to sort of do all of the layers that we want, and so that the channels actually make sense. So then we do the expand ratio to be expand ratio. It's going to be 1 or 6. Then we do the stride, and it's going to be stride if layer is 0. So we're going to downsample at the first of these multiple layers. So if we go to the paper right here, the layers so here, for example, we can see that it takes 112 to 56. So here we specify that the stride should be 2, but obviously we don't want to downsample at every layer. We only want to downsample at one of them. So what we're going to do is we're going to downsample at the first one for each of the ones that has a stride of 2. And remember, some of them has a stride of 1. So for example, this one, right, it has a stride of 1 because it doesn't downsample the height and the width. So if layer is 0, then we're going to use stride, else we're going to use stride of 1. Right, so only the first layer should have a stride greater than 1. For the kernel size, we're just going to use kernel size, and then the padding, we want to use same padding for all, right? The only one that downsamples is the stride. So we'll do kernel size. I'm just going to do this and I'm going to explain it. So this makes sense because we're using, so if kernel is 1, then we want to use a pad of 0, right? If kernel is 3, we want to use a pad of 1. Right, in this sense, in that way, it's going to be a same convolution. If kernel is 5, we want to use a pad of 2. Now, if you look at this simple formula, if it's 1 integer division by 2, it's going to be 0. 3 integer division by 2, it's going to be 1. 5 integer division by 2, it's going to be 2. So in that way, this makes sense. All right, so then we added that thing, and we're going to do that for each in the base model, for each stage. And for each stage, there are going to be multiple layer repeats, and then we go through that loop as well. Hopefully you're following. If you're not, that's okay as well, but just try to understand the details of this. We're going through the base model that we defined in the beginning, and then what we're doing is dependent upon the phi value, the width, dependent upon the version of the EfficientNet, the width factor and the depth factor is going to be different. So that's how we make it EfficientNet B0, B1, etc. All right, so at the end, we're going to do features.append. So append CNNBlock. This is going to be the last one. So it's going to be in channels, right? That's the last output right there. So we're going to in channels, then we're going to do last channels, and then kernel size of 1, stride of 1, padding of 0. Okay, and then return nn.sequential of features. All right, so what did we do? Well, we created the features, and that's what we called up here, right? So that created the features dependent upon the version of the model. Okay, what's left? Well, what's left is we're gonna do forward of some input x, and we're gonna use self pool of self features of x, and then we're gonna do return self.classifier of x.view x.shape of 0 minus 1, right? So before we send it to the linear layer, we want to flatten it so that we can actually send it through. And we want to keep the number of examples in the batch, but everything else we want to flatten. And then we want to run it through the linear layer with the dropout as well. All right, so let me just write a quick test, and then we'll make sure that this actually works. All right, so that's the test, and then we'll just run that test function. All right, so let me just explain quickly. Device CUDA, if it's available, we'll set the version to be 0. Then we want to get the resolution of the input image so we can generate some fake example. Then we'll set the number of examples in the classes. So let's just do it for 4 examples in a batch, 10 for the number of classes. Then we'll generate with number of examples, 3 for the channels, resolution. So that's going to be for B0 224 by 224. Then we'll call the model EfficientNet with the version and then the number of classes. And then we'll just print model x of shape, which should be the num examples, comma num classes as output. And as usual, it's probably not going to work. That would be a miracle. It's literally 175 lines. But anyways, let me run it and see. All right, so we got an error directly. We need to do toDevice on the input as well. And that actually worked. Wow, that's amazing. That's actually amazing. You gotta be applauding right now. That's amazing. Wow, that has never happened before. All right, so yeah, so that is EfficientNet from scratch. I tried this out on Cypher 10 and I got pretty good results. I'm pretty sure this implementation is correct, but I haven't trained it on ImageNet. Obviously, that would take a while. Yeah, but anyways, thank you so much for watching the video. These videos actually take quite a while to do, these paper implementations. So if you think this video was useful or interesting, then please smash that like button and subscribe. And yeah, I'll make more of these paper implementation videos. Just let me know what you want to see next. All right, hope to see you in the next video.